All right. So last session we spoke about vectors and how to create them and how to assign them. Vectors are going to be one of the big part of our programming. So I hope everyone got a chance to work with some of the commands for vector modification, creation, and assignment. Um, and that's more important because that's where you build up your next sessions on. So that's kind of important. And if you have not done or practiced any of these yet, do it before Saturday, because from now on the classes will pick up speed. We will have one class on Saturday morning and mid next week. So it's going to be at least 2 or 3 sessions from now on. So let's get into the gist of today's session. So last session we left off at creating factors. Factors is also one of the most important piece in our programming, because factors is a way you can, it's a variable which represents categorical data. So I'll give you one example just in a few minutes, which will clarify your understanding about factors. But factors is a way in R where you can represent categorical data. So it's not a numeric vector and it's not a character vector. It's categories of values, and the way you can have any vector factorized is by using this function factor of, and then you use the arguments. So within factor there are 3 arguments, and there will be more, but as if you remember, I told you that every function in R has a list of parameters. So a list of parameters, and every function you can look at the list of parameters by using the help section in R. So let me just open a new one here. So a list of parameters, the place to go for help with factors, or any of the functions, is to go and type here. So when I type factor over here, it's going to pull up documentation about factors. And if I just expand this part, you see that there are lots of other parameters for the factor function, and each one of these is different. So the more and more you practice this, you will get to know more about how to use these parameters, and you will be using these parameters a lot. But for today's session, we will deal with just the 3 or 4 parameters from this list. Okay, so let's go into one example which will clarify your understanding about factors. So there are three parameters within the factors. One is the actual vector. So you have to use factor, the vector name, and you have levels and labels. So levels and labels. So every parameter in R has a default value that if you don't give those parameters, it will by default contain certain values. So by default for factors, levels and labels are the same for factors. So let me give you one example without going too much into theory. So in this example, we are looking at categorical data. We are looking at directions and creating a vector called directions. And we are giving the 4 directions: north, east, south, west. Now, within the directions, there are these 4 values. So let me just check if anybody typed in any questions. Okay. So if I create a vector with the directions, then these are actually values within that variable, stored within this variable. So if I want to then create a factor of this particular variable, I use factor of, which is the function that I just told you about. You use factor of that particular variable directions, and you have two parameters. So this is the first parameter, directions, where you're passing in the vector, the variable or the list of vector. And you have two more parameters, which is levels and labels. So this coming to the second parameter, you have levels. So levels are actually telling you how many different unique variables, unique values there are within that particular vector. So just to clarify this point, I'm going to create one vector, similar vector. We'll call it directions, and I will enter north, south, east, and west. So this is the same vector that I just showed you, but sometimes you may have not this particular order, but you may have maybe duplicate values. Maybe you'll have another west or another east or something like that. So in practical data sets, this is what your vector will look like. You will have duplicate values. You will not have in one particular order. You will have triplicates or even more than that. So if I create a vector like this, and obviously my directions variable will have whatever I just created, all the values that I just created, north, west, south, east, west. So now creating a factor out of this vector, we have to use the factor function, then pass in the first argument, pass in the vector name, which is directions. Now what I want to do is set levels. In the set levels, what I'm going to do is I'm going to type in just the unique values within that vector. So I don't have to give the values, but I have to give just the unique values as levels, right? So I'm going to give north, east, south, west. You can give it in any order, so that order doesn't matter over here. We will come into ordered vectors in just a few minutes from now. But for this vector, directions vector, we do not have an order. So you just specify within the levels the unique values. And there is another. Any questions, anybody? Okay, so there is another parameter which is called labels. So labels, you can, somebody has their microphone there. Can you please mute yourself? Okay, thank you. So within labels is something that you want to name a particular factor as. So for ease of use, you do not want to use the whole you do not want to spell out the whole name of the direction. Maybe you just want to call them N, S, W, and E. Maybe that's what you want to call them. So you could actually label these values into a simplified value that you could specify. And right now what I'm doing here is labeling them as N, W, S, and A. So this way I can create a factor out of this. So what it does automatically is it's going to label these it's going to label the values within that variable as whatever labels you give it. So within R, it has a different way of storing factors. So within R, what R does is it stores the values of the factor as numerical values. So it's showing we are giving it north, east, south, west, but maybe R will store it as 1, 2, 3, 4, or something which is more convenient binary in a binary format, or may store it as a numerical value that way. So and so since we set levels to these factor variables, we can investigate levels separately from the vectors of from the values of the factor. So we will get to know about that in just a little bit. It may be a little confusing. I do not want to overwhelm you with too much theory. So let me go into the next one. So you have a lot of other functions that you can use on a factor once a factor is created. So let me show you one such function that you can use on a factor. So we just created a factor, but we did not store it into anything. So let me just store this factor in and call it maybe directions factor. Or you could just rename directions. So you could just call it directions. It's going to replace the vector directions with a factor called directions. So I just renamed, I just replaced the vector directions with factor directions. Now if you type directions, it's going to give us the labels instead of the actual values. All right, so the next function we want to try is you could use levels on directions. So these are the there are a multiple functions that you could use on a class factor. So in the previous sessions, if you remember, I used the function str for determining the structure of any particular value or any particular variable. So let's try the structure function on this directions and see what it gives us. So it's saying that the data type of this variable is factors with 4 levels, and the 4 levels are northwest, south, east. And as I told you just now, R, for its convenience, it's going to store it in a numerical format. So what it did here is it used the 1, 2, 3, 4 format. And there is another thing that is also useful, another function that you might want to remember. If you are unsure about what a variable class is, you could actually use the class function, and you could say class of directions. You could use either the str function, which gives in detail what the class is, and along with the class it gives what the values are, and it prints out the initial few values. Since we have only 5 values in this factor, it printed out all the 5. But if we have like 100 values in this, it's going to print out just the top few, maybe 6 or 7, top 7 values. And so suppose if you want to just check what the class of a particular vector is, or any variable is, you could use this class function. I use this pretty often. Instead of structure. When we go into complicated data structures, which may be like a list of matrices, or we will learn about more complicated data structures. That time, knowing the structure of that data structure is important, and sometimes it will give the class function gives the very top level data type of that variable. So you could use class. So coming back to the functions that we use on factors, levels is one function, and okay, so the other function is n levels, just to find out how many levels there are. If we have, suppose if we go on to have more than say 100 levels, or more than what you can count, it's always better to use this function n levels just to find out how many levels there are. But since we have only 4 levels in this, it's going to give us the number of levels, which is 4. But finding out how many levels there are, sometimes even like if you try to print out, it wouldn't print out the whole thing, because it's going to say it's going to print out maybe first 6 levels, and then it'll give a dot 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 dot. So this function n levels is important to find out how many levels there are actually within the factor. So if you want a subset of the levels, you can actually use this, but in practice we never use this. So let's go on to the next function. This is quite important function, which is the table function. So table is a very handy function. So it gives us how many of a particular value there exists. So here what we are seeing is with n there is only one value. With w there are 2 vests, right? If you remember in creating the vector, we did use vest twice. So it gives us a count, a tally of how many values there are in that factor. So what it gives us here is of the type n, there is only one value. Of the type w, there are 2 values, s1, e1. So table is a pretty cool function, and it could be used on factors as well as a lot of other things. Usually, if we want to find out within a data structure, within a matrix, in one column, if we want to find out how many different types of values there are, or so it gives us a tally or a frequency chart of how many particular values there are. So if you want to find out like how many zeros there are in this column, you could use the table, and it will list out how many zeros, and along with how many zeros, it's going to list out each and every value that there exists in that column. So you could try doing this for the data sets that I sent you last time, or you could also use it for the MT-CARS data set and try it on your own. Factors is something very important within our programming. So first is a vectors, and then is a factors. So let's move on to the next piece, which is ordered factors. So in the previous one, so I just want to pause here just to see if any questions there are. All right, so let's move on. So ordered factors. Ordered factors is used when you have a natural order between the values of the factors. So in the directions factor, you don't really have any order between. It's just 4 directions, right? There is no particular order between these values. But you may have, for example, you may have values like it may be ranked, it's low, medium, high, or you may have something like strongly disagree, neutral, agree, strongly agree. So there is a natural order between these, right? So whenever you want to capture this data structure within R, you have to be using an ordered factor, which implies that there is some sort of order between these values of the factor. And you can create orders by using ordered equals true. So it's this very same function as you used previously to create the factor, which is you use this factor function, and then you pass it the vector, the levels, and all this remains the same. But the only added parameter here is ordered equals true if you want to make a particular vector ordered. You can also make, like, if you want to make this vector ordered, you can still make order equals true, and it will set up a natural order between these, but it doesn't make sense over here. So let's just try giving an order in this for the status variable. So it's just low, high, medium. So so how many levels there are in this vector? Sorry, I just copy pasted it, so it's not recognizing my quotes. Okay, so in this status vector, how many levels do you think this has? Anyone? 3, yes. So it's just the levels are unique values in a particular vector, right? So the unique values are just low, high, and medium, low, high, and med, as it is called. So if you want to make a factor out of this, you use the method or function factor, you pass it the vector name, you give it levels, which is going to be the unique values in this vector that you're passing. And now, if you want to make it an ordered factor, you have to give ordered equals 2. So how do you recognize, how do you differentiate between a normal factor and an ordered factor? If you look at levels of an ordered factor, there is this sign, this greater than sign that determines the order. So now I had actually made a mistake here because I gave it the order, the levels as low, high, and medium, and that's why it's taking the medium as the largest one. But to do it the right way, I have to give low, medium, high. So because I'm giving the ordered equals true. Now you will see that it's high is the highest value, low is the medium value, and med is the medium value, and low is the lowest value. So now the order is right within these factors. All right, so let me see if there are any questions so far. Okay, so you could try this. So this is what we just tried. Let's move on to the next slide. So dates, working with dates. So we have covered, so far we have covered factors, how to create factors. We have covered ordered factors and how to determine them just by adding a parameter ordered equals true within the factors function. So now we'll move on to how to work with dates. So working with dates is very simplified in R. So usually it's more important for certain professions, like maybe a financial analyst, or a stocks analyst, are they work with dates a lot. But in research we don't use dates that much, but if it might be important. So one such real life example that I would like to quote from my experience is, suppose if you have different samples, and the sample, you are running an experiment, and the experiment cannot be run all on the same day, so you will run it in different batches. Now it is important to capture the date of these batches, because there might be some systemic bias between these batches. Suppose maybe a different technician is running it, or someone they're using it in a different time of a day, or something may happen. Suppose if different technicians are running it, then maybe they're not pipetting it correctly. Maybe one person is just pipetting right and the other person is is trying to extract the whole material with the same pipette, or they might have different practices. So the data is very sensitive to all these different changes. So that's why it's very important to capture the date of which that particular experiment or sample is run, or the batch type. So in that context, we do capture the dates, and it's important to be able to have a specific class in R to work with, um, dates and formats. So using a date class is nice to have in R. So let's get started with this example. So the default format in R is this format, which is a 4 digit year and a 2-digit month and a 2-digit date. So this is the default format. And you could change these formats by specifying different parameters, and which I'll talk about in a few minutes. But let's start with just the default format as of now. So here in the first line, what I'm doing is I gave it a date, and I'm using the function as.date. Okay, if you remember in the previous classes, we did talk about as.numeric, as.character. So any types you want to convert and you want to specify which type they have to be in, you use as.numeric, or as dot that data type. So similarly, date has a class, and let's just call it, you could call it anything, you could just call it X, and you use the as.date function, as.date, and the default format for dates is a 4-digit year, a 2-digit month, and a 2-digit date. So now I have X as the date, and if you want to find the class of X, it's a date class. If you want to find out the structure of X, it's a date, and the format is this. Usually structure gives you a little more information than class. And so I should be able to do something more than just defining it as a date class, right? So a date class has a lot of other functions that are associated with it. So one such useful function is this weekdays. So just to find out which day the date falls on, you use this function called weekdays, and you pass it the date class variable. So it's going to give us the day that particular date falls on. So that's a useful function to have. And any manipulations that you want to do to this date class, they're actually very simple. So one such example is this one, where you just add a number, or add an arbitrary number to a date class, and it's going to add so many days to that date, and it's going to give that particular date. Suppose in my case, if I want to add 5 days to my date class, it's going to take it, move that date by 5 days and give us the next day. So another manipulation you might want to do is maybe just list each one of the days, maybe for 5 days, right? So if you remember, you could create a sequence by using this operator, colon operator, right? So if I do 0, it means 0 to 5. 0:5 is 0 to 5. So it's 0, 1, 2, 3, 4, 5. So just one. So just one second, I have some questions over here. So right. So somebody is asking me a question that I had covered dates. So last week we had finished till vectors. So I had sent the slides because I had made it that way. We had briefly covered factors, but we had not done anything with dates. So I'm just recapping that one. So, all right, so you could create a sequence by using the colon operator. Now, how do we use this colon operator to create a sequence of dates? So you could just add that sequence to this, and it will display those many dates. So if you add 0 to the x, it's just going to display the current date that x has, right? If you add 1, it's going to be the next day. If you add 2, it's going to be 2 days after. So it's going to create the sequence of dates. So that's pretty cool to use. And so another way to do the same thing. So this is something. It's this weekdays function, which I already spoke to you about, right? So you could just use, if you want to list the number of the days of these dates, you could just use a function within the actual arithmetic that we just did. So x plus 0 to 5 gives the sequence of dates, and weekdays, if you use that function, you get the weekdays for these particular dates. So another way you could create, maybe you don't want to do a sequence of dates, maybe you want to do a sequence of dates, but they have to be 2 months apart. So this is one such example where you could use the seek. If you remember, in the very first session, or in the last session, we did talk about this function called seek, which will create the sequence based on whatever parameters you give it. So here we are using seek function to move the dates by 2 months, and how many dates we want to generate is 6. So you could use this function to create a sequence of dates which are 2 months apart. So you could try this on your own. It will generate a sequence of dates which are 2 months apart. And so one other cool function, you have this weekdays function which spells out the days of the week, and you have a function called months which will spell out the month that particular date class variable has. And you could use quarters function to determine which quarter it is, which of the 4 quarters it is. So there are pretty cool functions for dates. So if you're big on dates, if you need dates for analysis, you could use the dates class, and it has a lot of cool functions that you could use within your programming. So I just mentioned that the format could be anything, and you could create it in any way, and you could read the data in any format there is, and there are lots of options for you to make the right format of the date. So the default format, as I told you, is this format, but you could change the default format, or you could read the data and specify a different format by using formats like this. So what I have here is percent, and this is case sensitive formatting. So I have a percent sign, I have a lowercase d, I have a percent sign, lowercase b, I have a percent sign, and uppercase y. So these lowercase and uppercase do mean something, and the next slide will show that. And if you want to practice each and every one of these, you're free to do in your time. I'm just going to quickly go through these. So the capital Y, the uppercase Y, is the full 4-digit year, and the lowercase y is year without the century. So it's the last two of the year, last two digits of the year. And similarly, for a lowercase m represents the decimal digits. So it's 0, 1 to 1, 2, 0, 1 to 12. And uppercase B spells out the full month in the current local. Lowercase v represents an abbreviated month, such as Jan, Feb, MAR, Mar, April, APR for April. And similarly, for the days, you have the days of the month. You could lowercase d represents the number of the day, of the date, and similarly could use like the uppercase A for the full weekday name, and a lowercase a for the abbreviated weekday name, like MON for Monday, TUE for Tuesday, and so on. So these are the different formats that you could use. You could look up this on the internet and use it in the format over here to determine the exact date. So what we have here, the date format is 5th AUG 2016. So 2016 is specified by the uppercase Y, which spells out the whole year in the 4 digits. So that's this format. AUG again is an abbreviated month name, so it's specified by lowercase b, and the decimal digit is specified by a lowercase d. So you could look up the formats. There is no need to remember all these. You could look up the formats on the internet, and you could change the formats and read them as the data appears in your files. All right, so similarly, there is a time class, which I'm not going to go into details with, because time, manipulating the time variable and the time class is, it's a very specific field that people may use it for. Usually they do use dates, but if you need to learn about time, there's a class for that, and it's called as POSIX-CT. So there are 2 ways of specifying time, which is the the system time and the POSIX time. So in your time you could try out this, which is the way of specifying time. And again, within the time, the different formats can be specified by capital H, capital M, capital S for hours, minutes, seconds. So you could specify the time as that format. So similarly, as you do it in date, you could do the same thing for time as HMS. So I'm not going to go into details with this, but if you have any questions after doing this, please feel free to email me. And there are, I just put in some slides here, manipulating dates and times. So the 2 classes that we just read about, the dates and times. So if you want to practice these and ask me questions, you can do it. So that's the end of session 2. So let's go into the details of session 3. So session 3 is mostly some briefings about statistics and just for the people with non-statistical background. So I'm not going into details of each and every statistical method there is, but there are slides here. So go through this. Let me just go into the very basics. I'll just touch upon the basics here in the interest of time. So if people who already know about statistics want to sign off, you could sign off here. But the rest of the class is going to be just touching upon the basics of statistics. So usually in the data that we get is in different forms. So you have collected observations, you have collected it in the form of notes, surveys, or or experiments. And statistics is how you collect this, how you analyze it, and how you conclude, how you draw conclusions from this data. And what the typical process that we follow is how to identify. So first of all, we have a problem statement, or we identify what question you need to answer. Then you collect data related to that particular question. Then you analyze the data, and then you form your conclusion. So as you go through this, you may have three main questions. One is, how do we even collect data? So this data collection part is not the gist of our, or not the focus of our sessions, but we will go into details of the next two questions, which is how data should be analyzed, and what type of inferences you draw from the analysis. And so I'm just going to go into one case study, just give you an example of what data, how it comes, and what data is. Because if you are going out, setting out to be, statistical programmers or data scientists, this is the type of data sets that you will be dealing with. So this is one case study where it's treating a chronic fatigue syndrome data. So what you do, so in this, the objective was to give a particular therapy to patients and see if that particular therapy was effective or not. How do you even know that a particular therapy is effective? So in this study, what they did was they have this 142 patients who were recruited from different physicians, and out of the 142 patient population, there were only 60 of those patients who entered the study. So the patients who are determined to be eligible for the study, or who actually, so the pool is actually the number of patients who come inside the door, and the actual participants will go through several criteria. They have to meet a set of criteria to enroll in that particular study. So we'll have a subset of this population patient pool who enroll for the study, who are the actual participants in the study. So this is the typical way of study designs, clinical trials, or so most study designs. So what you have is two arms. You have a treatment arm and you have a control arm. So in the treatment arm, the people actually receive the therapy. In this particular case study, they are receiving a cognitive-based therapy. So the 60 patients who enrolled in the study were broken down into equal number of patients. So 30 patients were put in one arm and 30 patients were put in another arm. So the first arm is called the treatment. So these are the patients who actually receive the therapy. Sorry. And the other set of 30 patients fall into the control arm, or you may call it placebo. If the study is about a drug, the placebo arm are actually given some pill, maybe a sugar pill, just to have that effect. Maybe some people have a psychological effect that they are receiving the drug, and automatically they might get better. So they want to account for that. That's why in the first place the control arm is there. So in this study, what they found out was, in the treatment arm, sorry, there are two arms, treatment and control, right? So the outcome is whether the outcome was good or not. So this is the typical way you create a matrix of the results. So in the treatment arm, 19 of them came out with good outcome, and 8 of them came out with bad outcome, and the total number were 27. Although I said 30 and 30 were put, maybe some people dropped out, or some people may not have full data. So that's how you end up with. And based on these numbers, you can create the proportion of good outcomes. So if you look at it, the 19 people in the treatment arm represents 70% of the total 27. So 70% in the treatment group received a good outcome, and only 19% in the control arm received a good outcome. So how do you even, so to the naked eye, it looks good, right? You may think that, 70% compared to 19% is actually good. So treatment arm is probably much better. But you cannot say that with confidence. In statistical world, you have to put statistics around every numbers you see. So as I give you the example of, this is a very small example of, data matrix, but here is another data matrix that you might expect to see, like the first empty cars data set, right? So like that, this is another data matrix where, there are students in a particular class, and there are a variety of variables and data collected on these students. So it's number of students, maybe they are given roll numbers or whatever number, enrollment number or student ID or something like that, just to identify them uniquely. So every row of this is one observation and every column is a variable. So there are different categories of variables. Usually you have seen in the empty cars data set, you have seen a lot of numerical variables, you have seen categorical, you have seen character-based variables, right? So today, actually, we learned about categorical variables, and there are ordered categorical variables. So this is just a flowchart of the different types of variables there are. They just fall into two broad groups: numerical and categorical. So numerical variable, in numerical variable, you have continuous numerical variables and you have discrete values. What does this mean? A continuous numerical variable, maybe like temperature. Temperature can range anywhere between like 0 to 100 Fahrenheit, or some colder countries maybe even lower. So there is a range, and temperature can fall anywhere in that range. And discrete values, so there is a range and temperature can fall in anywhere in that range. So it may have like decimals and absolute numbers or decimals. So that is a continuous variable. And what is discrete variables? Discrete variables is whether you have either one or two, like the number of people in a class. You cannot have 1.5, or you cannot have those decimals. You have either a full person or no person at all. So that is discrete data. And categorical variables, you have regular categorical and ordinal categorical. Ordinal categorical is the same thing that we saw today as ordered. So ordinal represents some sort of natural order in the values of the variables, and there is regular categorical data. So these are just examples of these different variables, and each variable can be classified into more than one types of variables, which is fine, which is not a thing, but you'll just have to know in our terms how to deal with this particular data, or which class of variable do I put it in. Do I put it as a factor, or do I put it as a character? So one other main thing about factors that I forgot to tell you is, in statistics, factors are actually important, because in statistics, factors having categorical data is different from numerical or character, because the statistical models specifically need categorical data for some statistical modeling. So that's why in the first place factors were put in R, and it is important. Any questions so far? All right. So the relationships between variables, right? There are different types of variables, like, independent variables and dependent variables. If two variables have some connection or the other with each other, then it's an associated variable, or they can also be called as a dependent variable. If two variables have no relevance between each other, they are totally independent variables. Most of the time, the way most of our assignment or most of our equations work is you get an outcome variable, and that outcome variable is dependent on a few other independent variables. So that way, this dependent and independent terminology is important when you come to when you get to the point of machine learning or using statistical modeling. So we'll get to that point in some later sessions. So I'm just establishing the terminology now. And there are observational studies and there are experiments. So in observational studies, you really are not looking for outcome. You are trying to collect data, and you're trying to more like a monitoring setting. And experiments, you actually want a particular outcome from that experiment, or you have certain analysis set to do. So that's the difference between observational and experimental studies. So just to go into like the basic statistics thing, there is mean, median, variance, and standard deviation. Or something very basic to statistics. So if you haven't had statistics in a while, it'll be good to refresh your memory about what mean, median, and mode, and variance and standard deviation are. So mean is just an average of whatever values we have. So this is just a representation notation for a sample mean, which is where you add all the values and divide it by the number of values. So, and in statistical terms, a sampling mean is different from a population mean, and I would not get into the details of those, but as in when you encounter while doing a practice session, I'll let you know what that is. So variance is roughly variance is a measure of this or of the spread of the data. So it has this complicated formula, but you don't have to memorize any of these. This is something that you can go through. If you are interested, just Google that and try to know what it is. But it's not a requirement that you know about these for the class. And similarly, it's the standard deviation. So again, median is another statistical term. So in your free time, I just have these over here for you to just refresh your knowledge about these. So just one other thing. This I want you to know the quartiles and the interquartile range, because we will start doing box plots, and I will explain once again when we start doing box plots about what those quartiles mean and why is a box plot even necessary. But most times when you want to compare two different variables or two different values from different experiments, you use box plots to see if there is a difference in the two conditions. And this difference can be calculated in terms of you could just take the average of the two variables and see if they are different. But in statistical terms, just taking the average is not enough. You use the mean, you use the median, as well as you see how spread out the data is. So in that terms, the quartiles are kind of important, and I will explain once again when we start getting to the box plot settings as to what these quartiles actually mean. So just for now, you have to remember like the 25th percentile, which is the bottom 0 to 25th. If you have a range of data, say you have values, say 1 to 10, 1 to 2.5 will become the first 25th percentile of the data, and then 2.5 to 5 will become the um, 50th percentile of data, which is the median, and 50 to 75 will become quartile 3, and so on and so forth. And just the quartile range is the intermediate, the difference between, or the range between two quartiles is called the range. So don't worry if you cannot retain these. I will go through these once again when we are plotting out certain data, but I just want to set the stage now. So just to not go into very much details of what this bell curve means, and so the one thing that I want to take away from this slide is usually uniform data looks something like this, which is a bell curve, and there is right skewed data and left skewed data. So for uniform data, the mean is almost equal to the median. But there is right skewed data where the median falls, the bulk of the data is lesser than the mean of the data, and there's left skewed data where the bulk of the data is greater than the mean of the data. So why this is important? So usually in statistics, what is generally recommended is having data look somewhat like this, and which may not always be the case, because real data is real data. It cannot represent this curve here. So we use transformations, something like a log transformation, say, because log transformation always puts data into the standard bell curve format. So if any data we get, we always operate in terms of log transform data. So if we get raw data, we first transform it into log 2 or log 10, use anything, and it will put it into this bell curve. So the reason why we do it is most statistical models use this uniform bell curve data, and it requires the data to be in this format and not in this or this format. If they are in this or this format, all your statistics will be off. So remember one thing: whatever data you have to operate with, it's better to check before you start doing any statistics that the data is normally distributed. This is a normal distributed bell curve. So that's about the basics of statistics. There are some more slides over here. Again, this is something that you saw in the very first session, mean, median, mode. At that time, I did not say about what these mean, but you could learn it from the slide deck, or you could try to do some Google search on each of these terms to find out what these are, why these are important. But I have some basic slides here, so go through them. And from here on, we'll go into, we'll start this in the next session. So any questions so far? So if not, our next session is going to be Saturday morning, Saturday noon Eastern time. So it's 12 noon Eastern time, and yeah, and then we will. So are guys okay with having a session on Sunday too, or is it too close and will it not give you enough time to practice? Is Saturday and Sunday good for you? Okay. So if Saturday and Sunday is good for you, I think it's So it's going to be noon time, Eastern time. So Saturday and Sunday, at least you will have some time. Saturday, so the practice is going to be a little bit less. So I'll try to minimize the practice on Saturday, but it's better for you to just go through all the sessions until now. Just do your own practice, don't forget your practice, and we will talk about the upcoming test, which may be after 3 more sessions. So practice everything. I might give a small example program and try to test your skills. So that's it for today. Have a good night, everyone, and talk to you all on Saturday. Bye.